Hello and welcome, everybody. Thank you so much for joining us today. We know that time is precious. We want to get into the presentation. So today we have Brian Berkeley joining us. He is our Director of AI Data Platform here at Vast Data, and he's going to be going over our presentation of the Agentic AI revolution and the future of inference. Brian, you want to join me up on stage?
Love to. Here I am.
Hello and welcome. Thank you so much for putting this together. Really quickly for our audience, there is a Q&A box here over on the right-hand side. Please ask any questions as Brian is presenting. He wants to answer all of your questions. Anything you have, just go on and pop it right on over. So you see this Q&A over on the right-hand side, just ask your questions. He'll do his best to answer your questions. Okay, Brian, I'm gonna let you take it over. Thank you.
Excellent. Let's get that share going. Okay, here's the agenda for today. We're going to start with my take on agentic AI, why this wave is coming and what it's going to do for us. Then we're going to talk about BI in an AI world. So that's business intelligence and how it may change or be affected by the agentic AI. And then we'll get a little more technical. We'll talk about context window and how it plays an impact, and then KV cache and how it's not a solution to the context window problem, but how it's a useful tool in solving the limitations that a context window will provide. And then, of course, we'll talk a bit about VAST and why I think this VAST can help here, and we'll finish out with some Q&A. As Maria mentioned, there is a Q&A button at the top. I'm probably going to hold all the Q&A to the end. It's on my screen, though. I can see it. If you can't hear me well or something like that, go ahead and pop it in. Or if you don't want to risk forgetting your question, toss it in now. I will see it, but I will get to it at the end. First slide, I already stole it. I did not make this slide. It's a screenshot from NVIDIA's GTC keynote from Jensen. And it's talking about how we're shifting the original AlexNet moment, which kind of kicked off this whole wave of AI, and how first all we could do is say, in this image, is there a cat? And then we've moved into generative AI. And generative AI is what the world we're in right now. We're in the thick of it, and it's not going anywhere. We're going to be in the thick of it, and it's going to continue with us for a long time. But just on the dawn of it now, is this world of agentic AI, and we'll go into what that means. And then coming after that is the physical AI. You'll see just the early stages of physical AI today. There's Tesla's robotaxi might be an example of it. Google has Waymo that drives around. It's the robots that are going to be able to interact in the physical world, that are going to use the technologies from agentic AI in order to do that. I think someday we'll see physical robots. We'll have humanoids walking around, doing my dishes and folding my laundry. But that is a ways off. What's not a ways off is agentic AI. Generative AI today looks like this. As a user, like myself, I get to put in a prompt into AI. It will return me the answer, and then I go do the work. So in marketing, maybe I put in a prompt that says I want to generate some text for this marketing material I want to do. Then I go to another AI and say I want you to generate me an image. I pull those together. I make maybe a solution brief or something, and I then go off to do the work. But in generative or in agentic AI, as compared to generative AI, it's the AI that does the work. So instead of generate the thing, bring it back to me, it does the work. So, how do we use this? The first common things you're going to see in agentic AI is things like coding assistance. And we'll get into reasons of why I think that is. But in this example, I can ask AI to generate me some code. So I'm old. If anybody who's checking out my computer museum in the background there, I've been programming for a long time. I program a lot in Perl, and in Perl, you end up coming across a lot of regex, regular expressions. And I hope there's somebody in the audience that knows what I'm talking about. That it is difficult to do regex. I mean, I can do it. I can read it. It's logical. It makes sense. But when you want to, I got a list of file names. I want to strip off the date at the beginning of them. you create the regex in order to do the find and the replace. I could generate that using generative AI and describe, here's an example file name. I need a regex that I'll use in order to strip off the front, and then I go and do the work. Or with Agentic AI, I can say, I have some file names with the date at the front. I need the date stripped, and I don't have to specify that it's going to be a regex that I need. I simply let it figure out what the best method is in order to do the file and find and replace. And when it does that work, when it goes and makes the change directly, it can also see the impact of that work. It can see if there was an error message generated or whatever. If it forgot, like I have, to put sudo first because it didn't have permission to the file, it can see the impact of its change right away. And so in generative AI, where you get to create more, it gives you creative leverage. It can take some time and some toil out of doing generation tasks. Agentic AI gets you more operational leverage. You get to go from creating more to getting more done. I'll go into a couple more examples. In a generative AI example, I might say, generate me an image that I can post on X, and it'll do the generation, no problem. I'll probably have to give some details about what it is I want to generate, but you understand. In the Agentic AI, I can say, monitor my shower thoughts Slack channel. When there's a new post, generate an image-based meme using Flux. So I'll give it a tool access and post it to that channel, more tool access. If that meme gets 3 thumbs up, then post it to X. As you can see how it has more agency now. It has the ability to use tools. It can figure out the right way to do things, and it can learn from its feedback that images that aren't getting thumbs up often have something wrong with them, and those who do more like that, and then does the work of posting to X. If I use your more business example, often I will say things like generate a report based on last month's sales transactions. That's a normal thing that you can do. It's not even really generative AI. You can do all kinds of machine learning in order to get this, but it's something that you can ask to be generated. But in an agentic world, I can say, I'd like to know if last month's marketing had a meaningful impact on sales. So using your access to the sales transaction database, our Salesforce opportunity notes, the Zoom customer meeting recordings, the customer support emails, the website traffic analytics, and social media sources, determine the impact of the event, and then monitor daily for significant changes. So I think you can see that we're moving to a world where instead of just generate me some things, it's get more done. And what's interesting about that second side is that you, like in my regex example, you get to define the end state and let the intelligence of the system drive through the process. So let's take a look at BI or business intelligence and how that might change. We've been doing BI for a long time. And in BI, what you're trying to do is get to make data-driven business decisions. And so you want the best data in order to inform, to make the right decision. And so you're constrained by the technology landscape that you have. And so in most BI tools, the methods have been, you have lots of data. It's sitting probably on spinning disks. Those spinning disks are great at sequential read, but they're not very performant at a random read. So if your data is all over the place and different components, it's slow, and you're limited by how much CPU and memory that you have in order to do that. And the solution has been this wonderful ETL process, this extract, transform, load. So I extract my good data, whatever that happens to mean. Maybe it's, I want to look only at the last time period of a day, a week, a quarter, whatever happens. And probably out of that, I'm sampling. So give me 1 of every 10 and 1 of every 100. And then you move into your transform. So I want to clean that data. So if there's some sort of anomalies, outliers, junk them, get rid of that. If there is, what missing fields or something, you can get rid of those records. And then maybe you summarize. Instead of showing me all the transaction, just show me that store. What was the sales out of that store in that day? and often you normalize. So if I have a dozen different stores, maybe I instead of using the specific number for how many sales, I squash it into a percentage. So 100 being the best day they've ever had, one being the worst, and then you normalize it so all your stores have a consistent metric, and then you save that. You save the transform sequentially so that you can load it either immediately or at some future time into a database in order to do analytics. And this has been the best way. It continues to be a great way, and it's how many of the BI systems will always run, because it's useful and it works. And it follows this, what I'm calling a shrink to decide methodology, or the overarching theme, that you take all your data and you go through a distillation process in order to get the right data so that you can make the right business decisions. But AI is different because AI can think. It has intelligence. And so let's take a little bit of a step back and explain what that is and why I think that's so different. There's this concept of system 1 and system 2 thinking. There's a book by Daniel Kahneman called Thinking Fast and Slow, where he coined these terms. And all humans do this. Here's an example that if there's a bat and a ball are $1.10, if the bat is $1 more than the ball, how much does the ball cost? And if you're like me, your instant first reaction is that the ball must be 10 cents. It's 10 cents, the bat's $1 more. And then again, if you're like me, you get this like instant feel that it's wrong, or that it might be wrong, or that maybe I should double check my work. And when you do that, you slip from system 1 into system 2. It's more effort. It takes more time. And you think, well, if the ball was 10 cents and the bat's $1 more, it's $1.10. This didn't work out, right? So you do the math, and you find out the ball had to be 5 cents. The bat's $1 more, which makes it $1.05, and now you've got there. AI does the same thing. The system 1 type thinking is the information that's been stored in the weights of the model. You can feed a prompt in, do a next token prediction, and it just runs through the model it has and gives you some sort of snap judgment. But you can also kick it into an analytical reasoning. So this is what we often call test time compute, or the thinking period that happens during inference, where it can do a self-reflection and it can say, do I have the right data to analyze this? And it spends some time, maybe 30 seconds or whatever, trying to figure out and getting you the next token for the response. And that works in a chatbot type scenario where you want it to think for a few seconds and then respond. But you can also set it into a deep research mode. And if you haven't done this, I highly recommend it. Try to get access and do a deep research. You put in a prompt, and it goes off for maybe 15 minutes or even longer sometimes, and it pulls in hundreds of data points and web pages and other things that you might maybe give it access to, and it does a tree of thought and searches down different branches to try and figure out the right answer, and it comes back afterwards with this amazing and detailed report, because it spends more time thinking. And artificial intelligence is the first programs that we've ever had where the computer can do thinking like a human can. So it means we have to give it the right kind of information in order to do its thinking. So we're going to stick with this theme of our 1920s detective. It'll play out through the thing, and I definitely generated these images using AI. But so if we had our detective and he's asked to crack a case and he's given only the summaries. He has reports of eyewitness reports, and he's looking at those to try and uncap. It's difficult to find new missed information, new missed connections, new nuance in those summaries. But if instead we give them the raw data, so it's including voice or video recordings, maybe other forensic data, and he gets to pour over that information, he might get the aha moment. He might get the right connections made in order to make the right decision about what happened or what to do next. And so it goes with AI, that in the world where you want AI to be making recommendations and decisions about your business, and you want to make the best business decisions, you're in a different technology landscape. You want to have the largest model meaning the most neurons, the most parameter count. so that it can discern between different nuances easier. You want to give it a larger tree of thought and to spend more time exploring that tree of thought. So more compute time, more test time, inference, and more reflection loops. Do I have the right data? I do not. I'd like to go and get more data. I'd like to query this database. I'd like to read in that file. And in that world, it's just a world of more data. Instead of having a shrink to get the best decision, it's a grow to decide. The more data is going to lead to better decision making. So if more data is better, then why not just feed in all the data? AI can process a lot of data. What's the bottleneck? And it turns out that the context window is the bottleneck. So what do I mean by the context window? Let's start in a RAG pipeline, so a retrieval augmented generation. Maybe you want to pull a document from your repository. It's maybe a user guide or some kind of ground truth, and you want to ground the response that the AI will have in the context of that document. So that document becomes first in your context window. There's lots of other things you may want to use to grounding. So a chat history is another one. So if you're on like question 7 or prompt 7 or 8 or 10 or whatever in your chat, all the previous history needs to live in that context window, so that you can end up using things like pronouns, like no, not like that. Do it like the other one, or do it like our first one, or option 1 and 3 is the ones I want to choose. In order to have those things, option 1 and 3 mean something, you had to have the context of all the history, so it fits in. A lot of systems use what they call memories. I don't know if ChatGPT invented this, but this is how I experience the memories. And I can say things like, I want you never to use these types of phrases, or I prefer Canadian English spellings of words, being from Toronto. And then finally, your prompt. So all these things, your documents, your chat history, your memories, and your prompt, all get combined together in order to make your context window. And then that's the first step. So now you've packed together this context window. The AI needs to understand it. So it converts words into tokens, and then tokens into meaning. But how does it convert tokens into meaning? Imagine in this scenario, we want to have our model just finish the sentence for us. We're going to have some words, and it's going to finish out the sentence. Next token prediction. If I give it the word bank, it probably doesn't have enough information in order to finish out the sentence, or at least to predict what I wanted the sentence to be, because the bank can mean different things. So I think maybe most, at least definitely some of you thought when I say bank of a financial institution, but maybe there's some NASCAR fans out there that were thinking about what is the incline of the corner. Snowbank, whatever, up in Toronto. There's lots of different kinds of bank, and what do I mean? Well, how do humans figure this out? Just like I explained, it's the context. It's the words leading it up to and around that sentence. So if the sentence up to that point says, I found a great spot for a picnic on the bank, it might respond with, of the Potomac River. Or if instead I said, I need some cash, so I entered the bank, it might say to make a withdrawal, because the context of the words up to that point define what the meaning of that word is. And this is how the AI will calculate it. It does what's called self-attention calculations. And this comes from the transformer architecture. Not all AI are built on transformers, but the vast majority are. And so in a transformer architecture, it starts with the first token, and in this case, I, and does a dot product to try to understand some meaning of that word. Probably doesn't get a lot. It's only one word. And then the second one, so needed, it does another dot product of needed against I, and then needed against itself. So 2 more calculations. Sum has to do sum versus I, sum versus needed, and sum versus sum. And so you can see this grows. The longer the context window goes, the more calculations need to happen. on this slide, you can see there's a comma after cache, and the comma is another token because commas can change the meaning of sentences. Words with and without punctuation can mean different things. And so the same thing happens when you get to the token that is a comma. It does the same kind of calculations. At our 10th word there, the 9th word only took 9 more calculations. The 10th word took 10 calculations. But in the sum, to get to that point, the 10th word is 55 calculations. So you can see that it is growing. So there is a cost to self-attention. Self-attention is enormously useful. It is great at understanding the complex relationships, the nuances of language, and it's I was going to say the best, but maybe the only method really that understands the details of language in ways similar to what humans can do. But the context grows. Has enormous growth of calculation keys, so it grows quadratically. So it's limited by making sure that the context is in GPU memory. We'll explain the details later, but the GPU memory is much faster than even swapping out down to CPU memory, and so the context really has to fit inside that GPU, and it increases GPU utilization. So as your token list gets longer, as your size of your context gets bigger, there's more calculations per token, which consumes more electricity and obviously consumes more time. And it gets worse. Those tokens that you're having to calculate, what if you have to calculate attention keys for tokens that you've already read, you've already calculated attention keys for? Think of a coding assistant here. So if I'm asking the coding assistant to generate the next line, the next function at the end of my code, it has to read all of it. That makes sense. But what if I have a team of coding agents or a team of coding programmers who are all using agents? They're all making different changes to different parts of the code at the same time. Well, each of those processes are rereading the code over and over again as it keeps adding extra little bits and rereading the whole code again. You'll see the same in service support chatbots, where they will use a RAG pipeline to pull in things like a user manual and ground the response in the context of that document. And so that document gets reread every single time that a new prompt comes in, a new question. Or in fact, just in your long conversation with a chatbot, as you get deeper and deeper into that chat history, every prompt needs to start again and read through that context. And I imagine at this point, there's somebody saying, can't you just cache that? And yes, that is what KV cache is. That is the power of KV cache. KV just stands for key value, and cache is just going to store that computed information. So by way of analogy, and this is a crude analogy, it's not exactly perfect, but it's kind of the closest I come up with. If you were studying for school and you read through a textbook or some documents or whatever the first time, and then you wanted to re-look at that information later when prepping for an exam, it might have been helpful if you made notes in the margin or even underlined sections that were important. And that way, even without rereading the whole page, you can look up and it will trigger and you can remember the content on the page or the important thing that you needed to learn from that page. And so the same way with this KV cache, that you can store the computed result and not have to go and recalculate the keys. So whereas the key calculations will grow quadratically, that it will grow in a curved line going up, the size of the KV cache grows linearly. Yes, there's still more cache for each token. The longer the context window, the more you'll have to store, but it grows linearly. So as your context window gets larger, and it will get larger because we will have more data that we want to store, and we want to have that raw data in order to find new connections and new insight from, you'll have this growing delta between calculating and saving the calculated keys as a cache. The results are a couple things. So you definitely will get faster results. Instead of recalculating excuse me, instead of recalculating, you can just pull it in from storage, and you can and go from there. No recalculation necessary. But I think the more important factor is that it frees those GPUs from doing wasteful work. And so, do you want to reassign those GPUs to just servicing more people? More members of your organization can put in a prompt to the same GPU in the same amount of time, or maybe I wanted to give it more test time compute. I wanted to be able to follow more branches of my tree of thought, and so I wanted to pull in more data and do more thinking in that same amount of time. So I want to reallocate those GPUs into more useful work. You get to choose, but either way, I think that it will be quite useful to cache your context. Let's drill down one step into the data flow. As a user, you write a prompt. Whether this is generative AI or agentic AI, it starts the same. You put the prompt into the system of what it is you want done. And it goes into the GPU. The GPU then loads the model and the context into its memory. I'm oversimplifying here by saying the GPU memory, although I think it's really all that matters. But if we were to break it down, inside a host, you have a GPU, CPU, you might have some local flash, and then outside of that, you can have your extended storage cluster. And let's look at an example here of the large system, the NVIDIA NVLink NVL72 GB200 is a Grace Blackwell 200. It uses this super chip that has one Grace CPU for two Blackwell GPUs on a large die. And so in this NVL72, you get 72 Blackwell GPUs and just 36 Grace CPUs. And the GPUs all linked together on this giant backplane, and so they operate kind of as a single GPU. And so across the rack, you have enormous GPU capacity. You got 13.4 terabytes of memory and an unbelievable 576 terabytes per second of GPU bandwidth. And then your CPU or CPUs, there's 36 of them combined, will have 17 terabytes of memory at still fast but comparatively pokey 18.4 terabytes a second. And then your local flash. Now there's for each tray you've got 8 drives that you can put in there. And across all the trays, so you could, if you add it all up, you get 144 drives in the rack, but the drives are locked into the tray. Only the local CPU has direct access on a PCIe bus on all those drives. They don't link together by default into some large cluster. And so the speed, I don't know, depends on the drives you pick in. But if you want to move to your external cluster, where you can you can scale to exabytes or even zettabytes, and then it's just a matter of the speed of those network ports, how fast you can get data in and out. And on the current gen, it's about a terabyte a second. And I say current gen, but actually I think either now or in the very near future that'll double up to 2 terabytes. So let's go back. Our user put in a prompt, it went into GPU, and we're going to super simplify for the rest of the example of just GPU memory, because really that's what matters. It needs to be into the super fast memory of that GPU. And if you had that RAG pipeline where you've got to ground some response in a document, you use your storage cluster at the bottom in order to pop in that document directly into memory and have it in the context. It's unlikely, though, that you have a single GPU. And even if, so if you don't have the giant NVLink 72 GPUs, you may be using the Hopper series, and you've got H100s, and you've got 4 by H100 or an 8 by H100 linked together. But it's still unlikely that you have a single logical representation of the GPU. You probably have several H100s or several A100s or whatever it is. And so having a user send in a prompt to an individual GPU is not very efficient. And in fact, you'll have the user send a prompt into an LLM router, a large language model router. There are several of these. I'm not going to drive into the details. NVIDIA has Dynamo, VLM, an LM cache. There's lots of options in order to use. But the idea is the prompt goes in and then it routes that prompt to the right GPU. So what is the right GPU? You can see here we routed to the one that looks already busy. The two on the right seem to have the model loaded. They're ready to go, but their memory is otherwise empty and they're not doing anything. Why did I route this prompt to the one that has the context? And it's because it has the context. It already has the attention keys calculated up to this point. So if it's the next prompt in an ongoing chat history, you would want to send it back to the GPU that had the first set of prompts, because all the memory, all the information is already there and already calculated in the GPU memory. But what if that GPU memory is full? What if other people are using that same system and there's just no room to add in and grow that existing context? Well, then you're going to want to push your KV cache somewhere else. Now, you can push it back down to CPU memory. You can swap it in and out. If you think a conversation is cold, it can go down to CPU and then be popped back up to the GPU. But if you want to use the power of your cluster, you've got many of these GPUs, you're going to want to put it to some external system. And a global KV cache at the bottom tier seems to make the most sense. And so now that that LLM router, it will then go and talk to your storage and say, I know that you have this KV cache that's already been stored. I'd like you to populate it into a specific GPU host, which we will do, and then now you can route your new prompt into that GPU. So you can see this is the sort of modern scale out way in order to use KV cache to extend, to save on CapEx, to save on OpEx in a large GPU cluster, by making sure that you don't have to recompute the attention keys for context that you've already seen. Now, what storage would I want that lives underneath as that global KV cache? I'm probably a little biased, but and it's probably no surprise that I'll say it's fast. But this is why. So what if I was the one in charge of building that system? What are the key characteristics I would be looking for? And the first one is I want it to be linear scale out. I don't know what the requirements of my agentic AI workflows will be in a year or in 2 years. I know that it will be more. I know that the trend line is clear, and that it's going to want to have access to raw data in order to reason over that data and do some deep research on that data to come out with the best decisions. But how much data will it need and how much will we generate? I'm not sure. So I would want it to scale linearly as it goes. And how far do I want to scale? At least into the exabyte range. Maybe I'm not using that today. Maybe I'm in the petabyte range or whatever. But I sure wouldn't want to be the person who says to the company who's now leaning into agentic AI and they're putting more and more and more workloads onto that system that I'm sorry, we have to pause that productivity gain because I need to re-architect my storage layer. So I would want to find a system that can scale out and can scale out very large. I care about low latency and high throughput. So as my agentic workflow is doing that deep research and it's asked for more data and then stores a little data and asks for more data and stores another little insight, I want to make sure that it has access and it's not waiting for the storage each time. And so the technologies I'd look for is NVMe over Fabric, and it would have to have RDMA or GPU direct, so that I can get my content directly into the memory of the GPU and not have to go through the host and have that one extra hop on the way. I would care that my storage system is multi-protocol, block, file, object, but also database. If I want to have the agentic workflow accessing my data, I need to access it in the way that it's stored. And if those are in tables, if they're in databases, if they're in analytic systems, I would need that to be on my storage and need it to be available and accessible via my AI workloads. I would care about things like multi-tenancy. It's just a nice way to have separation and isolation. And in the same vein, I would care about QoS. I would want to make sure that some process, some deep research, some other checkpointing, whatever it happens to be, doesn't swamp and drain the resources of the rest of the system. And so your QoS for both max and min to make sure that nothing runs away and that everything has at least some access. I would want it to have zero trust security architecture. As we're bringing all these systems together in the agentic AIs to give them access to the systems, you would want to make sure that they can only get access to the things that they're supposed to have access to, and at the times they're supposed to have access to them. That just makes sense to me. And then, of course, you would want rich observability. And I don't mean just across the breadth of the storage system, although that's true, but you want to have it in the depth. You want to have it so that you understand, the workloads on the storage are coming from what workloads in an agentic AI system, and can I record enough information from there that I can generate a data flywheel, a feedback loop that says this kind of information is getting good results on that workload, and to sort of tune or preference or learn from that in order to have a better and more smarter, more intelligent system. And of course, VAST can do all those things. VAST is this linear scale out, exabyte scale, low latency, high throughput, multi-protocol, multi-tenant QoS, zero trust, rich observability platform that can handle all those kinds of workloads. A quick recap. I love these AI images. As we move from generative AI into agentic AI, I think the move is inevitable. And the reason I think of that is because of this concept of better, faster, cheaper, safer. This comes up a lot in manufacturing. It also comes up in computer engineering. That if the next product is better, faster, cheaper, safer, it becomes inevitable. It's a clear winner. If it's only one of those things, it probably still has value. If I make a product that is better than its competition, but it's not cheaper, it's more expensive, there's lots of cases where people will spend more money for better quality. But there's also lots of cases where people will want the cheaper. They'll prefer the cheaper thing, and therefore they know they're not getting the best quality, but it doesn't make sense for this use case or whatever. And in fact, this better, faster, cheaper often is it's a bit of a cliche where you say, here's 3, choose 2. You can make something better, faster, but it's not cheaper. Or you can make it faster and cheaper, but it's not better. But when you get all of them right, when you have something that is better, faster, cheaper, safer, it takes over. In my view, the typewriter was doomed. You could not. It didn't matter how good they made typewriters. In comparison to a word processor with a printer, the typewriter is doomed. Which one is better? I would argue that the word processor is a lot better. The ease in which you can make changes, not just, I typoed and fix it, but grab a whole section and move it to the top. You can't do that on a typewriter. Faster. I'm, again, old, check the museum. I took a typing class in grade 9 where you learned to type on a typewriter. And so I know when you want to center something on a page, the page is 80 characters wide, and you have to count how many are in your title, say, that you're trying to center, how many characters, including spaces, are inside that title, and then subtract that number from your 80, and then divide the rest, press the space bar that many times, and then type your title. Now it's centered. In a word processor, you type it in, you click the button, you hit center, and it's done. You could argue that it's not cheaper. Typewriters are fairly cheap, but if you amortize or you have a sunk cost of a computer anyway, or a printer for the floor of an office space, it probably gets to be cheaper and certainly safer. If anybody's tried, like, you've got some those arms, those keys have jumped up and gotten stuck, and you've got to go and put your hands inside the machine and pry them apart. You don't have to do that in a word processor. So I would argue that, in the physical AI, when we have self-driving cars, they'll probably be better, faster, cheaper, safer. They don't They don't text while they drive. They don't get tired. They don't lose attention. And so maybe not now, but in time, when the systems are perfected, they'll be better, faster, cheaper, safer. And for much of coding work, when I'm using Cursor now in order to do some personal projects, and in my own personal projects, I don't always do all the security controls or all the whatever. I don't really need it on my own machine, that I'm only the one using it. But Cursor doesn't know that, and so when it writes it, it does it the right way. And I only have to output, this is what I want it to be. A few seconds later, I get hundreds of lines of code. It takes me longer to read the code than it took to think about what the code should be and then write it. And the time savings is enormous. I think a lot of people are afraid of this feature. They think that the Agentic AI is coming, and so what does that mean for people, and what does that mean for our work? I'm not. I've been around. So when I started programming, there was people who that I talked to that had programmed in some of punch cards, but often in assembly. In assembler language, you have to know the architecture of the CPU. You need to understand the memory registers, and what are they, and what are they called, and how many, and what's the depth of the stack. You're essentially pushing the electricity around the chip. And when you go and write in C, you don't have to do any of that, because you have a compiler. You write in C in loosely English, and it turns it into code that then runs on that processor. And the argument was, well, then how can we ever really have great programmers? They'll never understand the architecture of the chip. And it turns out to not matter. It turns out that if it's easier to program, we end up with more programmers. If we have more programmers, we have more programs, and we have more solved with more problems that are solved with software. And so the whole level gets to be raised up. And today, when you move, it's not in C, you're using Python or Rust. And even in C, where you had to be careful about doing buffer overruns or whatever, and you don't have to now in Rust, for example. And so the result is you end up in a platform, in a paradigm that ends up being safer. It ends up being better, faster, cheaper. And do we still have great programmers? Yes, even though they don't understand the architecture of the chip. Do we still have people who do understand the architecture of the chip and can make better chips? Also, yes. And so I'm not worried. I think the same thing will happen. If Cursor is writing the code, we'll just have more programmers, which means we'll have more programs, and we'll have more excellent stuff. Does that mean we won't have programmers? No, you still need somebody to direct the work, at least for now. And so that's the trend I see things moving in, that the agentic AI is driving to this better, faster, cheaper, safer. And so it's an inevitable change, and every business will adopt it, and it'll apply it widely across. The why of better decisions for businesses live in the details. So if I look at let's go by way of analogy again. If a store has its sales lower, you can look at the summaries and the reports and try to ask, why is it that those reports are lower? And the answer might be that the inventory was too low, the shelves got empty, and we ran out of inventory, so the sales were low. And so you might make a business decision that says, get more inventory, like don't run out in the future. But if you had the AI that's able to have access to emails, to Slack, to all the systems in which you use and record that data, you may find out that Nancy, in purchasing, quit on the first month of the quarter. She went to a competitor because she felt like she wasn't being valued at work. And it took a while to hire somebody else, and they came in and they didn't realize the systems well enough, and it took them a minute in order to catch up, and they didn't get the inventory in time. And so the solution that you first came from the summaries was, we need more inventory, but the real answer of the why was that we need to take better care of our employees. And so the why lives in those details. Agentic AI loves data and will love pouring through and doing the work to find the right details and make better informed business decisions. But it needs access to that data. And the context windows are still the limiting factor. They're growing every quarter. I remember when we had 10,000 token context windows, they became 32,000 tokens, 128. I've seen million and even 10 million sized context tokens windows now, and those are mind-blowing. They're so much longer, and you can put so much more information in them. So that trend line is clear. The context windows are going to get larger because we're going to have more data to feed into these agentic AI systems. But that means the importance of KV cache and not recalculating, not wasting those cycles on that KV cache is even more important. And so what do I want underneath to store that super critical KV cache? Do I want to save CapEx by just being able to use my GPUs on higher value work, or do I want to accelerate progress by deepening the tree of thought and deepening the amount of data I have access to? Either way, I get to do that with VAST. The VAST AI operating system is that platform that you can be assured will be a right platform for your agentic AI workflow. Okay, that's it. That's the end of the formal presentation. You can find me online, send me an email, connect with me on LinkedIn. I am happy to connect and talk more, continue the conversation. Or you can do so in the Cosmos community. So at VAST, we have a community. It's both a web forum and on Discord. You can find me there. You do have to sign up, but sign up is free. So go to thecosmos.ai and you can connect with people there. Inside our Cosmos system, we also have labs. And the one being shown here is access to a real VAST cluster. You can log in, you can get access to the GUI, you can poke around, see what's there, see how it works, and get some real hands-on experience. And then jump over to the forums, jump over to the Discord, and talk with us more. Let's head into the Q&A. If you don't have time to stick around for the Q&A, I totally understand. I will be here to the end. But if you don't, there'll also be a follow-up email if you want to connect with us that way. You can fill out forms. You can respond to the email. You can ask for follow-up sessions, and we're happy to do that as well. But let me go through the Q&A. If Agentic can use tools, does that include search tools? Yes. The popular protocol being used right now is called MCP, Model Context Protocol. Originally developed by Anthropic, but it's an open protocol, so it's adopted broadly by a lot of different model providers, and that will allow the tool, the source of the data. So whether it's a database, Slack, whatever kind of system you have has your data. It describes what data it has and how to access it to the tool. You could also do the same for a search engine, so it can search the externally, and then you get to configure your agentic AI program that you've built to which tools you want to give it access to. Do you want to give it access to Slack, email, search the web, whatever it happens to be? When it has that access, then it can use those as part of its reasoning process. There was a question early on, sorry I missed it at the time, am I focusing more on inference than training? That's absolutely correct. The context window and the KV cache is definitely in the inferencing side. It's the reasoning and test time compute that happens after a trained model. Training of a model still wants lots of data, and VAST is a great platform to train your model on. But this presentation was on the inferencing side, the after the train. Where is the KV cache written to in most cases? So the KV cache is automatically, when it's calculated, and it's automatically created inside the GPU memory. And if you have enough CPU memory in the host, it makes a lot of sense to like sort of warm stage. If your chat protocol or whatever it is you're running is expected to have a history of interaction. So like a chatbot has a message, and then you wait some time, and then another message, and you wait some time. It makes a lot of sense to like temporarily push that from GPU memory down to CPU memory so that you can pop it back up when you need to. But again, that's localized to the host. So you, it's great for that machine. It's really great for routing those protocols, those follow-up prompts back onto the same GPU. But it's terrible for the other GPU that wants to access that information. That other GPU is going to have to pull it from somewhere. And so the best spot in my mind to put it is into a global layer at the bottom, a global external data storage layer that all of your GPUs are attached to. Your KV cache, you can still write it to your GPU memory and your CPU memory, but cache a copy down into the storage layer that all your GPUs can have access to. The typical connection between that, you would want to use an RDMA access, so GPU direct, and whatever type of GPU system you have, if you have on the new Grace Blackwells, you have lots of bandwidth. On the older ones, you have less, but you still have lots of bandwidth. And so you can build a cluster that will sort of match that line rate if that's what you like, or you can measure. Again, that's why I really love scale out. You can build for what you need now, and then you can extend that, as you need more capacity or you need more throughput, add on. Is it written in block or file or object? I think today the most common is written in file. And that's probably just because there's more history of using GPU direct of RDMA technology on file. I don't think there's any reason for it. I see a lot of push moving towards object and object-based RDMA. I think object is probably the right long-term solution. There's a lot of nice things to it that allows you to have it immutable. It allows you to scale out more programmatically callable. I mean, there's tons. Easier to push over wires. But I think it'll be today. It's predominantly file. I think in the very short time frame, it'll be predominantly object. I don't see block. Are these slides available for the audience? I don't have a problem with that. I don't know. Maybe Maria, if you're still around, if you can pop back on. If people want us to replay this or to have access to the files, is that something we can provide for them?
Yes, I can provide those the slides over email. So anybody who attended will receive the slides.
In all my AI generated pictures. That's great.
Yes. Awesome.
That was the end of the Q&A. I can still stick around for a few minutes. I'm very happy that you've joined. I'm hopeful that it was useful. And thank you for your interest in VAST and your interest in this technology. I see some interest in the recording links. Yes, it'll be in the email, I think, that comes out afterwards. You'll get that link. Okay, if that's the end of the Q&A, again, I thank you for your time. I'll probably stick on for another minute. I'll drop off camera, and I will otherwise see you guys online. See you in the community. I see the question. I was just writing a summary. Does KV cache have an expiry? Totally configurable, up to you. Your KV cache will become invalid if you ever change your model. So if you upgrade from like a Llama 3.1 to a 3.2 or something like that, or 4 now, the old KV cache will be different because it's a different set of neural network layers that it's going through. It would calculate the keys differently, and so you can sort of like mass invalidate and drop the cache. If you have space constraints, you could say, I want my KV cache to age out after a day or something. I don't know, like, or maybe, when I hit 90%, kill the oldest. You can set all those kinds of things. If you have the same model though, and you have the storage space, I'd say keep it. Maybe that document you read in as part of a context window, and you don't read it in for another month. But the cache is not super large. It's not nothing, but it's fairly easy to keep around, and so there's no reason that you have to expire it just because it's old. You can keep it until you change your model. No problem. Thank you.